So previously, we've seen how to convert between the coordinates for the standard basis, for Rm, and coordinates specified by another basis, let's say B. So now we would like to develop a general method for converting between the coordinates specified by the basis B and a third basis C. So to do this, we'll always pass through the standard basis. So first of all, we're going to define two matrices. C sub B will be the matrix with V1 through Vm as its columns, and the matrix C sub C will be the matrix with W1 through Wm as its columns. So if we're given a vector V expressed in the coordinates for the basis B, we can always convert back to standard coordinates. And then we can convert from standard coordinates to the coordinates given by C by multiplying by the conversion matrix for the basis C inverted. So this tells us if we take a vector expressed in the coordinates for B, we multiply that vector by the matrix whose columns are V1 through Vm, and then multiply that by the inverse of the matrix with columns W1 through Wm, then we can convert directly to coordinates in C. Similarly, if we're given a vector expressed in the coordinates for C, we can convert that to standard coordinates by multiplying by the matrix C sub C, and then convert from standard coordinates to the coordinates for B by multiplying by the inverse of CB. So let's do a small example. We're going to take two bases for R2. B is going to have the vectors 3 minus 2 and 2, 1. And C is going to have the vectors 1, 2 and minus 2, 1. So we have two conversion matrices, CB and C sub C. So I asked Sage for the inverses of these two matrices, and they are. So let's say we would like to convert a vector specified in coordinates according to B. If we want to express this in terms of our coordinates for the basis C, we can first convert to standard coordinates. Now, if we want to convert to coordinates for C, we can think about taking this vector, negative 25, 40, in standard coordinates, and we'll get, by multiplying on the left by C sub C inverse, the vector 11, 18. So we can see that we can do this operation in two steps. Alternatively, if we didn't want to do this in two steps, we could simply take the two matrices, C sub C inverse and C sub B, multiply them together. This will give us the matrix negative 1/5, negative 8/5, 4/5, negative 3/5. And if we wanted to directly convert the vector V in coordinates for B into coordinates for C, we simply multiply the expression negative 15, 10, right, that's a nice vector, by this matrix, and that will give us 11, 18 directly. Similarly, if we're given a vector that's expressed in coordinates corresponding to C, so 21, negative 49, we could convert this to standard coordinates first, and then we can convert from standard coordinates to the coordinates in B by multiplying the result by C sub B inverse. And we would get 19 and 31. And just as before, we could do this directly by simply multiplying CB inverse by C sub C. and then multiplying the vector 21, negative 49 on the left by this matrix. So as a note, we should observe that if we multiply these two matrices that we just converted together in either order, we'll always get the identity matrix. And this should not be particularly surprising if we view these conversions in the right way. So to do this, we're going to introduce a little bit of notation. So we're going to denote Rm with the subscript E, Rm with the subscript B, and Rm with the subscript C as the space Rm equipped with the coordinate systems for these three bases, the standard basis, the basis B, and the basis C, respectively. Now, it's important to note that as sets, these are absolutely identical. The distinction is merely psychological, so that we can keep track of our starting and ending coordinate systems. We can think about our conversion matrices as defining linear transformations. For example, we can think of the matrix C sub B as defining a linear transformation, which we'll denote as T sub B, comma E. So this matrix T sub BE takes in a vector expressed in the coordinates for B and outputs a vector in the coordinates corresponding to the standard basis. Similarly, the matrix C sub B inverse gives us a matrix transformation in the opposite direction. We call this one T sub E comma B because it starts from the standard basis and ends up in our basis B. It accepts a vector V and it multiplies that vector V by the inverse of the matrix CB. And it's easy to see that these two are inverses of one another. Similarly, the matrices C sub C and C sub C inverse should define transformations that convert from the coordinate system going with C to the standard coordinate system, and one that goes from the standard coordinate system to the coordinate system that goes with C, respectively. And just like with B, these two are inverses of one another. Unsurprisingly, to convert from one coordinate system, say C, to the other coordinate system, B, is simply a composition of these two matrix transformations. To go from the coordinate system defined by C, we first apply the transformation that goes from C to the standard coordinate system. Then we apply the transformation from the standard coordinate system to the coordinate system defined by B. So the direct transformation is T sub CB, which is of course also a matrix transformation, and it's defined by the product of the two matrices. So if we want to convert from the coordinate system defined by B to the coordinate system defined by C, we start by converting to the standard coordinate system, then convert to the coordinate system defined by C. Being a composition, this is again also a matrix transformation, and it is defined by multiplying the matrices that define the second transformation and the first. So now it's easy to check that if you compose either of these two diagonal transformations, then you're multiplying these two new matrices together. No matter which way you do it, the inverses will cancel from the inside out. And there you have it. That is everything for conversion between two bases.